Hi, everybody. Well, we're working our way towards being able to describe the algorithm for solving the problem of finding the closest point in two convex hulls. But before we do that, we need to formulate the problem in the most convenient way. And so this lecture is a little bit technical, but we're going to take the closest point in the convex hull problem and change it slightly so that when we, in the next lecture, talk about optimization, we'll be set up in the right format for doing that. Okay, so the optimization problem that we want to solve is the following. We're given two linearly separable sets of points, the plus points and the minus points, and they sit in a k-dimensional vector space. And we want to find points P and Q in their convex hulls so that the distance between those points is as close as possible. Now, we can make that a little bit more explicit by remembering that to give a point in the convex hull is equivalent to giving a point of the form sum lambda I plus xi plus, where the lambda i's sum to 1 and are all positive. And similarly, a point in the convex hull of the minus points, where again the sum of the lambda i's is 1 and they're all positive. And as lambda i's vary, these points will vary over the convex hulls, and so we can write the vector which joins a generic point in the positive set to a generic point in the negative set. And we want to consider the set of lambdas as lambda vary, so that either the distance or the squared distance as measured by the norm of this vector w is as small as possible. And we have the constraints that the lambdas have to be positive and the sum separately of the plus lambdas and the negative lambdas has to equal 1. So in a certain sense, we have a problem, an optimization problem in vector calculus here. Except that, well, let's make a few observations to see what might go wrong here. Well, first of all, there's some good news. If you look at this w of lambda plus lambda minus, it's the dot product of a vector with itself. And remember that the lambdas are the variables and the x's are, in a sense, constants for this. And if you work out this dot product, you see that you're going to get many terms which have lambda I, lambda j, maybe plus or minus, but only quadratic, together with dot products xi plus or minus, xj plus or minus. So the result of this dot product is just a quadratic function in the lambdas. Now, if there's 1,000 points in each set, you might have 2,000 variables here. But at least the degree of your function is only 2. You want to minimize a quadratic polynomial. That's the good news. The bad news is that the constraints that you need to apply are inequalities. Some are inequalities, some are equalities. I mean, they both have to equal 1, the sums. So those are the requirement that the sums be 1 is an equality constraint, but the requirement that they be positive is an inequality constraint. And Lagrange multipliers, as we talked about when we did the eigenvalue problem, is, at least in our original formulation, is well set up to solve the problem where you have constraints that are equalities, but not constraints that are inequalities. Now, there is actually a considerable generalization of the theory of Lagrange multipliers to handle inequalities, and that's a big subject, and it goes under the title of convex optimization. And there are whole courses taught on convex optimization. It's an extremely important problem, and if you go on in applied mathematics or machine learning, you will probably learn a lot more about convex optimization. But we're going to just treat this as a standalone problem and not get into that theory. Instead, we will describe an iterative algorithm for solving this particular problem called sequential minimal optimization. This was introduced in 1998, so it's actually relatively recent. But before we can get into it, we need to change our optimization problem a little bit so that it's more convenient to work with. So what does that mean? Well, I want to remember what W of lambda plus lambda minus is. W of lambda plus lambda minus is the difference of a point in the convex hull of the positive points and a point in the convex hull of the negative points as the lambdas vary over the allowed combinations of coordinates that are positive and sum to 1. And so originally we were just trying to minimize this function subject to the constraints that the sums were each individually equal to 1. Instead, we're going to change the function slightly by subtracting the sum of the lambdas, not requiring them to add up to 1, but instead just to add up to the same number. So each of these things here is now alpha. In the original problem, we required alpha to be 1, and they didn't appear in the objective function. Now we're putting them into the objective function, and we're not requiring that the sum of the lambdas be 1, but just that they be equal to each other. Then what we're going to show is that at the minimum, at the lambdas which minimize this new function q, the function alpha, which is the sum of the lambdas, is not 0. And if you divide the lambdas by alpha, so that now they do sum to 1, then you've got a solution to the original problem. So you would find the lambdas that solve this problem, divide them by alpha, so instead of summing to alpha, they sum to 1, and then go back to the original problem, and you would have found the closest points in the two convex hulls. And what we need to check is that these two optimization problems are equivalent, or at least that this one gives you a solution to the other one. So to prove that, let's first check that we don't have to worry about a bad situation in which we got an alpha equal to 0, because at the end we're going to need to divide by alpha. And the way to see that at the minimum value alpha is not 0 is to consider a very simple case where we set all the lambdas equal to 0 except the first one in the plus and minus. So essentially we assume that our sets only have one point in them. And we look at the function q on this special set of lambdas, and it becomes just a function of one variable, the variable lambda. And in that, according to that variable, if you work this out, you get that it's lambda squared times the distance squared between x1 plus and x1 minus 2 lambda, because w of lambda plus lambda minus in this situation is just x1 plus lambda x1 minus. And when you take the norm, you can pull out a lambda squared. And if you do a little calculus and you take the derivative and you set it equal to 0, you find that the minimum value occurs here at 1 over the distance squared. And if you plug that lambda in, you find that q takes a negative value at that minimum point. Well, what this tells you is that the minimum value of q is negative. It's not 0. But if alpha were 0 and all the lambdas were equal, that must mean that all the lambdas are 0. They're positive and they add up to alpha. So they all have to be 0. So at the point where alpha is 0, q is 0. And we've just shown that's not the minimum. So if we find the minimum value, it's going to have a non-zero alpha. Now we can actually check that the two problems are the same. And to do that, we can use the fact that we have to keep straight three things. First of all, we have lambda plus and lambda minus, which minimize the q function and satisfy the constraints of problem 2. Then we have sigma plus and sigma minus, which minimize the w squared and satisfy the constraints of problem 1. And finally, we have tau plus and tau minus, which we get from the solution to problem 2 by dividing by alpha. And what we want to show is that these all give the same minimum value for q. So let's start by noticing that if you look at tau plus and tau minus, since they satisfy the constraints of problem 2, and lambda plus and lambda minus give the smallest possible value of q among points satisfying those constraints, that q of lambda plus lambda minus, which by definition is w lambda plus lambda minus squared minus 2 alpha, must be less than or equal to the value at tau plus and tau minus, which is w of tau plus tau minus squared minus 2, because remember, for tau plus tau minus, alpha, this is 1 over alpha lambda plus 1 over alpha lambda minus, and alpha is the sum of the lambdas, so the sum of the taus is 1. So the 2 alpha becomes just 2. Now, the second thing we can notice about tau plus and tau minus is they satisfy the constraints of problem 1, because they sum to 1 and all the lambdas are bigger than 0. But sigma plus sigma minus is the value that gives the smallest value of norm w squared among those that satisfy the constraints of problem 1. So w tau plus tau minus squared also has to be bigger than w of sigma plus sigma minus squared, because by definition, this is the minimum value. Similarly here, this is the minimum value. Okay. Now we use the fact that there's a kind of homogeneity. If you take w of alpha sigma plus alpha sigma minus, then remember what this is. This is the norm of the sum of alpha sigma I plus xi plus minus the sum of alpha sigma I minus xi minus. And when you multiply the vectors by alpha in the norm, you can pull out an alpha squared. And so this is alpha squared times the norm of w sigma plus sigma minus squared. And we already showed in the previous remark that this is less than or equal to w of tau plus tau minus squared. So we multiply both sides of that inequality by alpha squared, which is, of course, positive. But now we can put the alpha into the norm, multiply both of the tau plus and the tau minus, in the same way here that we pulled it out. And therefore, when you multiply the tau plus and tau minus by alpha, you get lambda. And so we end up with this inequality as well. And now we subtract 2 alpha from both sides of our previous inequality, and we get w of alpha sigma plus alpha sigma minus squared minus 2 alpha is less than or equal to q, because when you subtract w lambda plus lambda minus squared minus 2 alpha, you get q. But now we use the minimality one more time. We know that this value here, by definition, gives the smallest possible value of q. So if alpha sigma plus alpha sigma minus give an even smaller value, they must give the same value. In other words, it has to be the case that this side has to equal that side, because it can't be any smaller. This is the smallest it can be. And if this side equals this side, you can cancel the 2 alphas, and you find that this inequality that I had shown up above is actually an equality. In other words, the tau plus and tau minus that we got from problem 2 gives the same minimum distance as the sigma plus and sigma minus which we got from problem 1. And that shows that tau plus and tau minus that we construct by taking a solution to problem 2 and dividing by alpha gives the minimum distance to the problem where we just looked at the distance itself. And as we'll see in the next lecture, this problem is easier to work with.